Okay, welcome to example 14 in our functions and graphs topic. We're looking at the third type of non-vertical asymptote. So if you haven't watched example 12 and 13, please do so, because there's a journey that we're on. And this is the third type where the order of the numerator polynomial is greater than the order of the denominator polynomial. So you can see in this example here that this function here, the numerator's got order of 2, a square term, and the denominator's order 1. That's going to produce what we call an oblique asymptote. Now the example here says investigate all the asymptotes of the function, which means that we should be considering the vertical asymptote and the non-vertical one. Now what I'm going to do is I'm going to investigate the oblique asymptote first, so that if all you want to do is learn about that, that's great. I'll then go on to just remind you about the vertical asymptotes, even though we've covered that before, just so that the example is full. But if you've come here to learn about this third type, I'll do that bit first, okay? So what we want to do is very similar to the one we did in example 13, okay? We want, because it's order 2 divided by order 1, we know that it's going to end up being oblique. But we can prove that by doing a little bit of algebraic long division. So our function starts off as 2x squared plus 3x minus 2 all over x plus 3. I'll use my line tool because I don't trust myself to draw a straight line that long. So we want to think, what is that in terms of partial fractions, or in terms of, not partial fractions, but remainder, quotient and remainder. So we'll have a look at doing a wee bit of algebraic long division. We're dividing 2x squared plus 3x minus 2 by x plus 3. Okay, so again, we take the highest order term in each of those expressions and divide them. 2x squared divided by x is 2x. So I'm going to put that here. And then I'm going to multiply through 2x by x plus 3 gives me 2x squared, and then 3 times 2x is plus 6x. And I'm going to subtract that from the expression up above carefully. So 2x squared minus 2x squared is 0, that's good, and 3x subtract 6x is negative 3x. The order, it matches up. We haven't got to a point where the order of our remainder is less than the divisor, so we can still go another round of algebraic long division. So I've got negative 2 as a constant term. We're basically dividing negative 3x minus 2 again by x plus 3. So negative 3x divided by x is negative 3. So if I multiply negative 3 by x plus 3, I get negative 3x minus 9. Okay, and we want to subtract that, and we end up with, I don't know why I drew a line in between there, we end up with negative 3x subtract negative 3x is 0, negative 2 subtract negative 9, negative 2 add 9 is positive 7. Okay, so that's my algebraic long division technique. We have a separate topic on that, partial fractions, where I go over that if you are not sure. So what have we got? We can rewrite our rational function. The whole point was to get a quotient, which is 2x minus 3, plus a remainder, which is plus 7 over x plus 3. Okay, I'll call that y, just because I tend to consider the x and y coordinates more than f of x. So again, we want to investigate the equation of the asymptote. So we want to think, okay, when x tends to a very large number, what happens to the y coordinate? Well, as x gets very large, obviously 2x still gets large with it, minus 3. Effectively, this is still a valid connection. Okay, so as x gets larger, the y coordinate follows the rule 2 lots of x minus 3. Okay, the interesting thing again happens with this fraction here, because as x is very large, 7 over x plus 3 tends to 0. So we can say that's basically it, plus 0. In other words, y tends to the expression 2x minus 3. Tends to, but remember that that 0 is actually just a fraction. Well, we don't know actually, it might be a fraction above or below, but it's just a fraction off of 0. So it tends towards the value, but isn't exactly the value, and that's why our asymptote is the point where the y coordinate never gets to. But that is the nature of the asymptote. So we can write down, therefore, there is an oblique asymptote. Now, Oblique. Get it spelling right, please. Asymptote with an equation. Now, y equals 2x minus 3. Do you notice that the line has to have an equal sign, but we can never say that the y coordinate equals 2x minus 3 because it will never do that. But the equation of the mystery line, the invisible line, can have an equal sign. So we can draw that in with our dotted line. We'll draw it, so it's obviously got a positive gradient, so it looks something like that, and we can write in y equals 2x minus 3. Okay, that's us got the, we've proven the equation of the oblique asymptote. Again, we want to check the nature. We want to investigate the nature because we want to check as x gets large and negative, and as x gets large and positive, where is it? Is the y coordinate below the line or above the line? As x is large, but is it above or below the line? That's the thing that we never quite know ahead of time. So we've got to investigate it. How do we do that? Two things. As x gets large and positive, as it tends to positive infinity, what happens to the y coordinate? Well, we're back up to the idea of y equals 2x minus 3 plus 7 over x plus 3. We've already investigated most of this, so we can say that y is going to be effectively 2x minus 3 plus 0. Now, this is the point. See up here I put plus or minus because we didn't know. Well, we do know in this case, because when x is positive and large, it's going to tend towards a positive 0 value. It's just going to be slightly above 0. 7 over 1,000,003 is 0.000 something, but it's positive 0.00 something. In other words, we can say that as x gets large and positive, the y coordinate follows the rule 2x minus 3, so it should be on that line, except the plus 0 plus bit takes it just fractionally above the point y equals 2x minus 3. In other words, the curve is going to tend towards the asymptote and stay above it. And if we think about when x is large and negative, then again it holds to the rule y equals 2x minus 3 plus, and this fraction is still almost 0, but when x is negative, 7 over negative 1,000,000,000 plus 3 is still going to be a tiny fraction, but it's going to be a negative one, so that 0 negative pulls it below what the value would be if it were on the rule 2x minus 3. In other words, it's going to be below the line, and the curve is going to kind of behave in that way there. So we've discovered that the nature is, on the left hand side of the graph, the curve will come below the asymptote, and on the right hand side the curve will tend above the asymptote. Okay, again we've worked out the nature of the non-vertical asymptote. So that's, if you want to go off and you're practicing that, that's great. I'm going to finish the question because I did say investigate all the asymptotes, so if you want to stay with me then that's great, because we want to check out the horizontal asymptote as well. And of course, as we found out way back in kind of example, I don't know, 10 and 11 I think it was, they're quite easy to investigate. So there can be more than one, remember, because it all depends on, oops, oh well, we've got a dotted line here. Horizontal asymptotes, Oh, why am I writing horizontal? We're checking the vertical asymptotes. There's more than one. I can't talk and write at the same time. So, vertical asymptotes exist when the denominator is equal to 0. Okay, and in our situation here, the original denominator was x plus 3. In other words, when x equals negative 3. Okay. Now that doesn't, you haven't answered the question about the vertical asymptotes. You've just said they exist when the x coordinate is negative 3. There's a very subtle bit of logic to say, although the answer to the vertical asymptote is the same, you have to state that you're now moving it to be an equation. So we can say the equation of the vertical asymptote is x equals negative 3. Okay, we can check its nature. So we've now got a second asymptote, a second dotted line, and so we'll draw that. I always like to draw the dotted lines. It helps to have an illustration, I feel. So this is the equation x equals negative 3, and this time we want to check whether the curve tends on the left hand side and the right hand side, whether it tends up towards positive infinity or down towards negative infinity. So what do? Let's write down, it's been a while since we saw the function. F of x equals 2x squared plus 3x minus 2 all over. Yeah, I tried to draw a line and it didn't work. 2x squared plus 3x minus 2 over x plus 3. Now, when we were checking out our vertical asymptotes, it was helpful to have everything factorized. So I'll do that so that we can, it makes it easier to think about the signs of the different factors. Okay, so we factorize the top line. It's got to be 2x and x. In my first term, that would give us 2x squared. The constant terms have to multiply to negative 2. So you might have whatever technique that you use for that. So it's going to be positive 2 there and negative 1 there. And there we've factorized our numerator. Why do we do that? Because we want to think about as x kind of is approaches negative 3 from below, and we want to think about as x approaches negative 3 from above. In other words, to the right and to the left. So this is below, to the left really. Okay, so as x tends to negative 3 minus, what happens? Is the y coordinate very large? Is it positive? Is the y coordinate negative? Well, we can use this function to help us. The y tends to, well, let's put a value just below negative 3 in here. Okay, so the first factor, 2x minus 1, if x is negative 3, let's say negative 3.1, then that whole expression is going to be negative. The right hand factor, x plus 2, if we're dealing with a value of x like negative 3.1, add 2 to that, it's still going to be negative. And if we check our denominator of x plus 3, this is the linchpin one, this is the one that's going to change. Because for negative 3.1 add 3, it's still going to give us a negative value. So overall, our y coordinate is going to be positive divided by a negative, which will produce an overall negative value, which tells us that it's going to be effectively our y coordinate is going to tend towards negative infinity, which means our curve is going to be on the heading down the way as it approaches the asymptote. And if we have a look at x tending to negative 3 plus, in other words, when x is just to the right of negative 3, just greater than negative 3, like negative 2.9. Let's have a look at the expression. So go back to our factorised function here. If about negative 2.9, double it, take away 1, it's still going to be negative. Second one, x plus 2, still going to be negative. And the x plus 3, if x is about negative 2.9, add 3 to it, it's going to become positive. So we're going to end up with a positive term on the top, a positive term on the bottom, which means that the y-coordinate is tending to positive infinity. In other words, it's going to be up at the top. So on the right-hand side of the dotted line, my curve is going to be above at the top of the line and not down at the bottom. Okay, so now I've investigated the whole function. I've got two asymptotes. I've got a vertical asymptote here, and previously I investigated the non-vertical asymptote. So that's what you would have to do in order to fully investigate the asymptotes of a function. It's long, but the more you do it, the quicker you'll be able to analyse any of these functions. Okay, I hope that's been helpful. And we're going to go on and have a look at how we could sketch a whole function using some of this knowledge that we've got.